Good morning, everyone. Time for our next session, this time from Mathis. He's going to talk to us about building bandwidth estimation into Pion. Pion is a fantastic project around in WebRTC. I won't explain it. We'll wait until afterwards and talk to Mathis about it. So what's next on my agenda to talk to you about? So we've got lightning talks tomorrow. So that's on Thursday for anyone watching on demand. If you're watching on demand and it's already Friday or Saturday or even a month's time, then you've already missed out and you should have watched live. So if you're interested in doing a lightning talk, it can be about absolutely anything that's relevant to this industry. Then get in contact with us, team@concon.xyz, or talk to us on Matrix, and we'll get you a slot for tomorrow or Friday. So generally you get 5 minutes to talk about what you want to talk about. And then we'll have a bit of a chat afterwards, and then we'll move on to the next person. So that's that tomorrow, and then tomorrow and Friday. And then we've also got drinks tomorrow night as well, where we can all get together and have a bit of a drink. No matter what time zone you're in, it's a good excuse to have a drink of whatever, tea, coffee, whiskey, gin, whatever, at whatever time it is tomorrow. So talking about sponsors very, very quickly, we've got Subspace, Daily, Element, and Mux. There are platinum sponsors, and our gold sponsors, Taloo, 100 milliseconds, and Dite. Silver sponsors, Lowway, Sangoma, Millicast, and WebRTC Ventures. And then our community sponsors, Jambones, Telecurve, and Pion. And then our AV partners. We've got PSP, Millicast, Broadcaster, Subspace, Element, Mux, and Meet Echo. Without the help and support of all of them, this wouldn't have been possible. So go say hello, go say thank you. They're the reason why this conference is completely and utterly free of charge. So I'm going to pass you over to Mathis's recording, and then we'll be back in about 22 minutes for a bit of Q&A. So see you then.
Yeah, hello everyone. Thank you, Dan. Today I'd like to share with you my experience in implementing bandwidth estimation from scratch for the Pion project. First, a little bit about myself. I'm a graduate student at the Technical University of Munich, where I currently work on my thesis on congestion control for real-time media over QUIC. And for the past couple of years before that, I've been a backend developer, and I've been mainly using Go for the recent years. So when I started my thesis project, I also tried to use Go as much as possible because I really like the language. And then I headed out to find some projects and existing libraries that I could use for my project. And I quickly found the Pion project, which is a collection of real-time communication libraries written in Go. And it's the perfect match for my experiments because I can just pull in all the libraries from Pion that I need for my experiments while ignoring all the other WebRTC features that Pion provides, but that I don't need in my research. Today I'd like to share how I integrated bandwidth estimation in Pion, which I'm obviously experimenting with. And yeah, then let's start with a short recap about real-time media on the internet. We usually use the real-time transport protocol, and here's a very high-level overview of how that works. On the left side, we see a media sender, which produces some media stream from a source, for example, a webcam or a media audio feed from a microphone. This media feed then goes into a media encoder, which produces an encoded stream. The encoded stream can then be packetized in RTP packets, which will then be sent over the network to the receiver using UDP. The receiver receives the RTP packets, decodes the data from it, and can then play out the media, for example, show a video on a screen or play audio on a speaker. Then next to RTP, we also have RTCP, which is the RTP control protocol. RTCP can be used to share synchronization information or give feedback about the network performance from the receiver to the sender. A little more detail on the network between the receiver and the sender. Then the packets are typically traveling through a lot of routers in between on the internet. And these routers, if they can't push out as many packets as they're receiving at the same time, they use some internal queuing. And here we can see that this queuing leads to, for example, packet loss if the queues are filled on the router, or it can lead to different delays. The more queuing is employed in the router, the bigger the delays will be. And in non-real-time communications, when we try to find out how much data we can actually send from a sender to the receiver, we can just try to push as many packets out until we see some packets being dropped, for example, from overfilling queues. And then we can reduce our bitrate and use this mechanism to send as many packets, but reducing loss at the same time, and just retransmitting the packets that we lost. However, in real-time communication, we have another requirement here, which is that we also want to have a low latency. So of course, we want to share our media in as high quality as possible, but the latency should also be very low so that we can actually have an interactive communication with our partner over a video conference, for example. So how can we use the information which we can observe at the receiver from the internet, from the network in between us, to find a way to send as much data at low latency at the same time? And here I've shown some of the characteristics we can observe at the receiver. First, there's the inter-arrival delay, which you can see on the right side. For example, the delay between the first and the second packet are very short, and one packet may be dropped, and which is also something we can see at the receiver. And then the delay is getting bigger between 4 and 5 and 5 and 6. And that typically is a sign that there's queuing going on in the network and that the queues are growing. And then there's also the one-way delay, which is also increasing as the queues are growing, but it's a bit harder to measure at the receiver. So now, how can we use this information which we have at the receiver to calculate a bandwidth which we can use from the sender? Luckily, there aren't a couple of algorithms already available which you can reuse, so we don't have to invent them ourselves. I have listed 3 of them here, which are specifically made for real-time communications. The first one is self-clock rate adaptation for multimedia, or SCREAM. Then we have network-assisted dynamic adaptation, or NADA, and then there's also Google congestion control. Before we can implement any of these algorithms, we of course need to know what the receiver has observed from the network at the sender side, so that the sender can decide how much data to send. And for that, we can use some feedback format. We have 2 formats already defined again. One of them is RFC 8888, and then there's another one called transport-wide congestion control, which was invented for Google congestion control. And both formats share pretty much similar information, which can be sent from the receiver to the sender via RTCP. And the information contained in these packets is which packets have actually arrived, like packet acknowledgements, and at what timestamps have they arrived at the receiver. So in this feedback format, for example, we can see packet chunks which contain information about the acknowledgements, and then we have received deltas in the end which contain information about the inter-arrival delays, which I showed earlier. TWCC is already implemented in Pyon today. We have released this earlier this year. And here's a little overview about how TWCC is actually implemented in Pyon. So Pyon has a concept called interceptor. Interceptors are used to transform RTP and RTCP streams. And here's an overview about how interceptors work. You can chain them together. For example, we could have a receiver report interceptor in the top. Then we have our TWCC interceptor in the middle. And then the RTP, RTCP streams will be written to the network, or in the other direction, read from the network. Or we could also have, of course, other interceptors afterwards. Then the interceptor for TWCC is interested in incoming RTP packets because it is keeping a log of the incoming packets and at which timestamp they have arrived at the receiver. And this receive log can then be used at a regular interval to create feedback reports, which will be sent to the sender via RTCP from this interceptor. So now that we have feedback in place, we would also like to have some tests set up so that we can actually evaluate the implementations we built for Pyon. And of course, it's always hard to find a good simulation of the real network, because it's hard to know what the network in reality will behave. So we need some way to model this in our test setup. And one way of doing this is to create a virtual network interfaces on one host, so that we don't have to use physical machines, we just use one machine. On this host, we can run, for example, containers to easily assign virtual interfaces to them, and then we could use tools like traffic control for Linux and network emulation for Linux to apply different traffic shaping mechanisms to these interfaces. For example, we could limit the bandwidth outgoing of one interface, or we could randomly drop packets at a certain probability, or we could add some delay to the interfaces. This setup is actually one that I'm using for my research experiments. But for Pion, we wanted to be independent of the operating system, so we tried another approach. And Pion has a concept called VNet. VNet is a library that was developed in Pion actually for testing NAT setups and connectivity in NAT setups. It is a full virtual implementation of the network, and specifically of the network packages in Go. So the software which uses the network package usually can replace this network package by VNet, and then instead of sending the packets out to a real network interface, we just keep them internally in this virtual network layer. VNet currently supports only IP and UDP, and it virtualizes network interfaces and then has internal routers so that we can set up different complex network topologies to emulate different networks. Since it was only developed for NAT testing in the beginning, we had to add some simulation for network impairments. And for that, we have created a token bucket filter for mimicking bandwidth limits. And we have implemented very simple filters for adding delay, which is just an internal queuing mechanism, and then also a simple filter for adding loss. We're currently using this setup in the first tests for our bandwidth estimation implementation. It has, of course, some drawbacks. So it is not a real network stack, and it doesn't implement TCP, for example, for testing cross traffic. But we still hope that we can use it in the future to test the basic functionality of different implementations, and to have some testing in place, which is independent of the operating system below. Then a word about the test cases we're actually implementing. There's another RFC already defined for that, which defines different cases which should be tested for evaluating bandwidth estimation algorithms. Here's just an overview of one example case. For example, we could have different sources on the left side, which will send data to some router, A here in the picture. The router will then forward the packets to router B, which will distribute them to different receivers on the right side. And the shared bottleneck between A and B is what we're using to test the behavior of congestion control algorithms of the sources. The test cases can then implement different characteristics on the network in this shared bottleneck between the sender and receivers. For example, we could limit the bandwidth, we could change bandwidth limits during test cases, and we can, of course, also have different setups. In this case, we have senders and receivers on the left and right side, but we could also use only one sender and only one receiver. We could share data in both directions, so bidirectional flows. And then we can, of course, also have cross traffic in either UDP or TCP, which is non-real-time traffic, so uses different congestion control algorithms. And of course, our congestion control should also be able to work with this kind of parallel traffic. When we're testing our implementations, we of course also need some data to send. But today there's, at least not that I know of, any video encoder in Go. So we still need some data to send in Go, and we could use two mechanisms for that. Either we could integrate a video encoder from another language, or instead of integrating another language, we can just use some random traffic. And for random traffic, there are there's another specification which explains how random traffic can be sent in a way that models a real video encoder. That is, of course, still a bit different from a real encoder because it's always hard to predict what a real encoder would do, but at least it gives it an approximation of how a real encoder would act in the test case. So now with testing and feedback in place, we can start implementing our own bandwidth estimation in Pyon. The first thing we have tried is to implement a version that is already existing. So we don't implement our first algorithm ourselves, but we rather use one from another implementation in another language. And the first one I used for that is Scream. Go has CGO, so CGO allows us to integrate C code in Go. This works like this on the slide here. So you import a package called C, and before that in the lines you can use C code, and then later in the code you can use C types by writing C dot something. And this is an example in the slide here, which uses the Scream receiver, which is called Scream RxC in this case, and everywhere where we use c.scream RxC, we are actually calling the C code. And the same thing, of course, works for the sender side. And the Scream receiver here in this case then sends feedback in a RFC 8888 form and is not using the TWCC format we are implementing in Pyon. Then the implementation for the bandwidth estimator is integrated in Pyon again using interceptors. We have here an interceptor for bandwidth estimation, and so that we don't have to use different interceptors for bandwidth estimation implementations, we just write one interceptor which uses a common interface for all the bandwidth implementations on the right, like Scream, Nadar, and GCC. And in this case, the interceptor is interested in the outgoing RTP packets to record what has actually been sent. And then it is also interested in the incoming RTCP feedback from the receiver, so like RFC 8888 or TWCC. The bandwidth estimation algorithms, Scream, Nadar, and GCC, or whatever you want to implement yourself, then provides an interface to update the application with the estimated bandwidth, and this application can then use the estimation, for example, to use a lower target bitrate for the encoder, or reduce the resolution of the video or frame rate, or increase it, of course, if the bandwidth is available. Then I've said on the earlier slide that we want to use the same interceptor for all the same functionalities for different bandwidth estimators. So we defined an interface in our Pyon implementation, which has to be fulfilled by all the bandwidth estimators. We have a pacer interface and we have a bandwidth estimator interface, and the bandwidth estimator one is the most important one, I would say. It's for recording packets as seen on the slide before and recording the feedback incoming from a receiver. The on-packet send method is recording at which point in time has a packet been sent and how big has the packet been. And the on-feedback method records at which time has the feedback been received and gets a packet result. And the packet result is just a type which abstracts away from the wire format of TWCC or RFC 8888 so that we can use the same feedback format for all the bandwidth estimators. These interfaces are a bit simplified, so some parts are missing, which are not that important in this case to show off. And in our implementation, they are still work in progress, so they are still very experimental, and we might change them in the future because we only have the Scream implementation yet, and we are working on a Google congestion control implementation. Then there's also the pacer interface, and the pacer is useful to avoid sudden packet bursts, to send high bandwidths at a very short time and then being silent for a longer time afterwards. And the pacer basically has a queuing interface, type of interface. It has an enqueue method which just enqueues the next packet to be sent, and then the sender can use get pending packet to queue for the next packet to send on the network all the time. Then the next thing we are going to do is we are implementing Google Congestion Control. Google Congestion Control is split into 3 components. The first one is a token bucket pacer, which works as I explained on the slide before. It's just a very simple implementation right now in our setup. The next part is a loss-based congestion controller, which basically works by looking at the loss observed by the receiver. As long as the loss is lower than a certain threshold, we can increase the bit rate. And as long as it is higher than a certain threshold, we can decrease the bit rate. And all the times when we receive feedback and the losses in between this range, we just keep the bit rate as is. Then the delay-based controller is not implemented in Pine yet. We're planning to do that by the end of this year or early next year. And the idea of the delay-based controller is very similar to the loss-based one. As long as the queuing delay, which I talked about in the very beginning of the talk, is increasing, we know that there is queuing going on in the network and we can reduce the bit rate. And as long as the queuing delay is decreasing, we can increase the bit rate. Okay, then we have some future ideas which we would like to implement in the future, but we are currently still working on the Google Congestion Control implementation. But then in the future, we would of course also like to have native implementations for Scream and NADA. Then there's the other feedback format, which I talked about already, RFC 8888. And we would of course also like to implement this feedback for Pine so that we can use different feedback formats with all the congestion control algorithms. And then there's probing, which I have not talked about yet. Probing is used to probe higher bandwidths without having the encoder configured to higher bandwidths. So if the encoder is still outputting a low bandwidth or bit rate, then we can use extra probing packets to probe for a higher bit rate. And then 2 concepts which could make this stream more robust is forward error correction. We could still implement flexible forward error correction, our setup later, but that's something we have not spent time with yet. And then there's another concept called adaptive forward error correction, which uses forward error correction packets to probe for higher bandwidths. And that's also something we would like to look into in the future. With that, thank you very much for joining this talk. I hope I could show you about how a little bit about why we need bandwidth estimation in the first place, how it can be implemented, and then of course what exists today in Pine and what we are planning to implement in the future. Thank you very much.
Thanks so much, Mathis. So I'm going to bring in Mathis, real Mathis in right now, real-time Mathis. Oh, I haven't muted myself. Hold on 1 second. I'm going to accuse myself. There we go. Sorry about that. And so, yes, Mathis is here with us, and he's got a small update. Like the talk was recorded, I think, about 3 weeks ago. So I'm going to pass over to Mathis for a small update on the work that he's been doing, and then we've got a question from the audience, which we'll follow up with. So over to you.
Yeah, hi, good morning. Thanks. So yeah, we have a short update. I have to say I've changed the interfaces I presented a bit, especially the pacer interface has changed. We're using now something that we pass packets directly to the pacer and gives the pacer a writer where it can write the packets to and then send it out by himself. And then we have prepared a test runner, which automates the tests I presented earlier. And we run in this test runner the Docker tests and the Go unit tests. And we're working on a little interface, a dashboard-like interface, which we can use to present the results of all these different tests we're running. So much for an update for now.
Cool. I mean, I'm no bandwidth estimation expert at all. It's one of those like things that I know of within the WebRTC world, obviously, but actually how they work is just mind-blowing to me. So Andreas has a question for us. Does bandwidth estimation also make sense with audio only? taking into account it doesn't take a lot of bandwidth. I'll pass it over to you because I've no idea.
Yeah, I think it's hard to say whether it makes sense. In our test cases, we use constant bitrate sources for having some audio sources next to the video sources. And yeah, given they use not a lot of bandwidth, I would say probably makes less sense than for video. And yeah, that's what we're using in our test cases. If there's an audio encoder which can use variable bit rates and in a very limited bandwidth session, maybe, but I'm not sure about that.
Then at the same time, you could if you chose to, you could send a lot of audio, and very, very nice audio as well. So
yeah.
I think as time goes on, it will become more and more applicable, let's say, because people are wanting to do more with say WebRTC audio, being able to send music and know that things are going to arrive at the right time, etc.
Yeah, that's true.
Yeah. Well, thank you very much for joining us. Thank you very much for the session. It's one of those sessions that I feel like I need to go back and watch like 3 times to really consume all of the information. So that session will be on YouTube, so everyone can watch afterwards to their heart's content. I think that's it for this morning. We'll be back later on today. So thank you very much, Mathis, for getting up early and joining me. And then for everyone else, if you're watching on demand, i.e. on YouTube, make sure you like and subscribe the channel. It means we can do some extra things. And if you're watching it live, then go over to YouTube anyway and press the subscribe button and the bell button because it helps. And you'll get a nice alert saying, this session's next. Anyway, thank you very much, and we shall see you in the next session.